All right, so allosteric enzymes have quaternary level structure. This came about from these guys, these French scientists. I know that Jacob Monod and I know that I've heard some of their names before in courses of genetics and stuff like that. They did other things with bacterial transcription and things like that. But for the purposes of this, they also came up with this model to explain allosteric enzymes. And what this is all based around the fact is that allosteric enzymes have multiple active sites. So that's the basis for this, is that allosteric enzymes have many ASs, active sites. Another thing that this model kind of brings forth is this thing known as the symmetry rule. And the symmetry rule just simply states that both, for your enzyme, both the subunits and the actual active site, they must be in the same conformation. Same conformation. No, you can't really see that. Well, what are the conformations that we have that they can exist in? Well, there's two, and they're existing in equilibrium. So there's the R conformation. I like to just call it the R conformation. It stands for relaxed, but I'm not going to write that down because personally I think that's moronic, and you'll understand why I think it's stupid to call this the relaxed conformation, because this is the least stable one. This is the catalytically active one. This is anything but relaxed. The other conformation is known as the T conformation. Again, it stands for tense, but I think that that's stupid because it doesn't really tell you anything. This is less catalytically active and therefore more stable. Less catalytically active and more stable. And yeah, these guys exist in equilibrium. So because of the symmetry rule, if you have substrate binding to the R form in one, this is going to, of one of your substrates, or one of the active sites, sorry, this is going to cause a conformational change in all of the enzyme active sites to convert to the R form. And that's what the symmetry rule kind of implies, is this actually says all active sites are coming in here. So when substrate binds to the enzyme of one active site, then all active sites are going to go ahead and convert to the R form. They all become R. And that's what, because of the symmetry rule there. So what I'm trying to, I guess another way that I could say this is that when a substrate binds, whenever we have this, the equilibrium is going to, should probably draw that, that's equilibrium shifts to the R conformation. This kind of goes about this process known as cooperativity, which is where if you have a quaternary level, in this case an enzyme, but it also applies to proteins as well, once one of them starts to convert to a different conformation, all the other ones are going to convert to that same conformation because it's like a chain reaction thing if the conformational changes. There are ways that we can, however, modulate and mess with this equilibrium. So I'm just going to go ahead and write over here, modulating equilibrium. So modulating equilibrium. So there are two things that we can do. We can have negative effector molecules, or we can have positive effector molecules, and I think you know exactly what we're talking about. The positive effectors are obviously going to stabilize the R state, so it pushes equilibrium to where it says R favors. Okay. The negative one, as you can imagine, stabilizes the T state. So this is going to be T state. This is said to have a heterotropic effect, or heterotropic effect. So if I were to just go ahead and along this, and I probably should have color coordinated these, but if I have a positive effector molecule, say that I go ahead and do, here's my graph, here is my sigmoidal curve of my allosteric enzyme. Well, with the use of a, just write it like this, with the use of a positive effector, this curve is going to kind of shift from here to the left. So it's going to look a little bit more like this, and that's a really bad drawing. I'm trying to make it look like an S here. I guess that's not terrible. If you could see, imagine that all being one thing. But anyways, the curve shifts to the left. I know, it's weird. The curve shifts left in the R favorable states because of positive effector molecules, if you think about that for a second. And then I'll do the T, I guess these ones in whites. These have homotropic effects. What that means is that it has homo, meaning same. So you get the same curve, right? As you would for that of a regular enzyme. And then it's going to kind of shift to, well, as you can imagine, to the right. I feel like we're using so many substitutions and abbreviations, it would be bad to to let's say R because of the conformation series. But anyways, this is what it's going to look like. So here's again my graph here. Here is my sigmoidal curve. Well, as you can imagine, this is affecting it. This is a negative effector. It's going to favor the T state, and so it's going to have, whenever we draw it here, it's going to look like that, if that makes sense. It's moving to the right. The Km value is becoming at a larger substrate concentration. This lowers the Km value. Another word that's used as this is the threshold concentration, because that is, and I feel like that's not really helpful in terms of understanding this, because threshold concentration, however, is just saying that this is the concentration at which, the concentration of substrate at which it's not as sensitive to changes so much, and that's kind of just synonymous, I think, like with Km. So there's really not much of a point in talking about that. But anyway.